So you see, maybe you could say last 2-3 classes, what have we been doing? Well, if you want to say in a technical word, it's just L'Hopital's rule. Yeah, we were focusing on L'Hopital's rule. I think 2 classes. Yeah, L'Hopital's. But obviously we did much more. And what we really did is, if you think about it, in the last 2 classes, is we were developing techniques to show existence of limits, right? Using the existence of limit of derivative, right? So mathematically, that's what we really did. And let me write that, okay? So we developed techniques. And this is really, if you think about it, a deeper way to show existence of limits, right? Techniques to show existence of limits via, I'll just say via mean value theorems. That means by analyzing the behavior of the derivative, we showed existence of limits and hence calculated and so on. Specifically, we use the Cauchy mean value theorem, right? This was the thing. So basically, from existence of limits of the derivative to existence of limits of the function itself, right? So existence of limit of some f dash by g dash with some conditions, and we solve that. A limit of, I'll just say derivatives. We went from here to limit of the underlying function. Okay, this is what we have seen so far. Then along these lines, when we were doing this, we encountered the following question, right? So we encountered, or we rather arrived at, naturally encountered the following question, which was similar to one of the questions we had seen. So if it's given to you that limit x going to 0, fx plus 1 by fx, yeah, if this limit is 2, okay, then again the question is, does limit f exist? It's a similar question to these things in the sense that a limit of something related to f is given and you're asking the limit of f exists or not. Okay. Then does limit x tend to 0 fx exist? Okay. So here let me just say this condition that f maybe is a function from r to let's be very safe and say half to infinity. Yep. So this was kind of a homework I had given last time. It's not a very simple question. So let's see if someone has done it or not. So this is a this question we want to discuss, and through this we want to explore some theory, which we have not done. So f plus 1 by f, this goes to, together it goes to 2. But then does it imply that f must go somewhere? Obviously, if it goes somewhere, it has to go to 1. That is very simple. But the main question is, does it exist? Yes, yes. Mm. So let me write that. So limit uh, xn for this xn, no, just as a limit n tends to infinity, right? And okay, that is, I don't know, we can probably use how will we use? Yeah, that is, so this will be true. So does everybody know this? That, I mean, this is in the definitions almost, that if limit, understating it, we will not prove this. If limit x goes to 0 is equal to something, it implies that if you take any sequence to 0, right, it implies that limit of uh, n tend to infinity xgn will also be L for any sequence xn that goes to 0. Yeah. So this is a much, so the first statement is a much stronger statement. It says that if you go to 0, you know, by using all the numbers in the neighborhood, go towards 0. And if you kind of tending to L, then if you go to 0 on a special sequence, okay, you jump towards 0 by a special sequence as n tends to infinity, then also the limit will be the same. Okay. Does everybody know this as a fact and intuitively understand this? Not asking for a proof. If anybody doesn't know, they can say. Okay, so let's move on. I'll keep it there. Yeah. Okay, then what do we do? So we know this, that this is a special sequence, and we know this. So what can we say from here? Can we say that limit f of 1 by n exists? Okay, so you are saying that might be fun. Yeah. So you're saying like this, fx plus 1 by fx minus 2. Okay, then what do you do? Oh yeah, okay, okay. So I think I understand. You're saying it like this. Okay. Yes. Yeah, roughly speaking. Okay. Either mod fx is very large, or yeah, that's roughly, that's there in the thing, right? But can we say from here that limit of f has to exist? So that is just, I think, completion of squares. No, this is right. No, in the denominator there will be no square, right? Just check the manipulation. Just, yeah. Is this correct? So just verify this, right? This is, yeah, just expand it and check it. Yeah, it will come something plus 1 minus 2 fx. Yeah, you see, you get this. Yeah, this is correct. This is fine. This is, but then will this be useful is the question. So remember, if the limit of f exists, then it has to be 1. Maybe you can use that. I mean, yeah, how will you use that? It's Hmm. Yeah, that's the point. Yeah, that's right. And you can even see it directly through here, right? That f cannot really be large. But then how do you quantify it? So let me write a more precise phrase, okay? But which will again not be precise enough, but we'll at least understand the need to make it mathematically precise and come to the things we need. So basically, what I'll say from here is uh, no part of f can remain bigger than 1. What do I mean by this? I mean that if you consider f on the like graphically, then let's say this is 1. Yeah. Then as you move towards infinity, right? Even if f is, let's say f limit of f does not exist, right? But as you move towards infinity, this portion of f that is going above 1, right? Yeah, this cannot continue to happen, right? So even if you get a sequence where it is more than 1, then you have another term where it's again more than 1. So you may find these terms where f is more than 1 for some time. Oh, no, so this is going to 0. I'm sorry. What should I do? I'll just change this to infinity just to explain now. Okay, I think it'll be just easier to explain. Nothing will change, so don't worry. Yeah, you understand. So eventually, so it cannot remain bigger than 1 as you go to infinity, right? The parts that are bigger than 1, they will actually have to come closer and closer to 1. Right? So no limit. Even if f has different limits, if you take different sequences going to infinity, you may get different limits for f if limit of f doesn't exist, but they cannot be bigger than 1. Right? So I travel along any sequence going to infinity, then the corresponding sequence for the functions, that sequence cannot be bigger than 1. It kind of has to go towards 1 or less than 1 maybe. See, this is the intuitive picture. Right? So let's just change this question to going to infinity. It will just make more visually. I mean, I can do it at 0 neighborhood, but it's more easier. Just for the time being, because this doesn't give any new interpretation as of now. So you can use it if you need it. So I'm trying to say is that for any, so it seems like, right, for any sequence xn that goes to infinity, right, f of xn kind of has to eventually, has to go to, if it goes somewhere, then it has to go to somewhere, something which is less than equal to 1. Right? But then similarly, it has to go somewhere which has to be bigger than equal to 1. I mean, if it goes somewhere, right? If you take a sequence xn that goes to infinity as n goes to infinity, and then you look at the corresponding values of f, right? If those values are are less than 1 and less than 1, then even this is no good, right? It has to again, it cannot remain less than 1. right? It has to approach 1 kind of, or bigger than 1. Because again, if something is less than 1, then this thing will become bigger than 2, right? So this kind of is intuitively saying that it should be equal to 1. But where is this intuition not equaling the mathematics? That is what you have to ask and then think. I mean, we'll do it now, but take your time, think. Yeah, I've just made xn, I mean, I've just made x tend to infinity. Yeah, that's basically this 0 was only a formality. It works for anything, but it's easier to explain for x going to infinity. Yeah. I mean, it could be anything here. That doesn't matter. Okay. So then I think what I said right now was not very helpful. Okay. Let me say it in a different way. Okay. So since we are going to approach this problem via sequences, and you will see how Bolzano Weirstrass will come in. I mean, I'll state it for those who have not seen it, but even then the proof will look very tricky. Okay. But we'll see how to make it not look tricky. See, what the plan is, okay, the plan is to show that we will show, so we'll show for, we will show that for any sequence xn going to infinity, which means, as n goes to infinity, we will show that for any sequence, meaning that no matter how you go towards infinity, f of xn goes towards 1. So this is in the same spirit as we will do this problem using sequences. Okay, so remember, our goal is to try to show, so I mean, I suppose for all of us it's almost clear now that the limit does exist and it's equal to 1 by the explanation, right? It can't really escape to something more than 1 and can't escape to something less than 1 also, kind of. But still something is missing. We don't know if those limits exist or not, right? If you take a sequence going to infinity. But I'm just now saying the same thing more formally. The question is, does limit f of x exist as x goes to infinity? We are just translating this to, we'll show that for any sequence going to infinity, this limit is 1. Now, this is the same thing because you know that if limit x going to any point exists, then that's the same thing as saying that any sequence you take to that point, the limit should exist, right? So this is a result which we are using. And this is, again, intuitively, you can see that it's very clear. Maybe you have not proved it. You can try to prove it. Limit, so this limit exists. This means that for any sequence, I have not stated this before, this is the other direction also we are using, for any sequence xn that goes to A. So you go to A via some number or you go via any sequence. Okay, limit. So again, this is not a repetition, partial repetition, but I've not stated this earlier. So is exists. Let's say is equal to L, then this will be L. So the converse is also true. You see, this is the fantastic part. If you know that for any sequence going to A, this limit of this is a sequence, is going to L, and the same L, okay, then you can also say that the limit exists. Okay, for those who have not seen it, please, if you don't understand the statement first, yeah, you can say, but intuitively it should make sense. But first, see if you understand the statement. So there are two directions to this, okay? Yeah. Hello, I lost your voice. Oh wait, is my connection? Hello. Oh, he left the meeting, I think. Yeah. Connection issue. Okay. Is everybody? Yeah. Mm-hmm. But what are we proving? Which one? Which one? This one you're showing for any sequence? Okay, so can you say again how you are using, how you are doing it? Okay, so let epsilon be greater than 0. Okay. Mm-hmm. Why? No, no, no. But no, no, no. 1 minute. No, no, no. Xn will have because x is going to infinity. No, no. But this doesn't make sense, right? Because x is, what is x? X is a variable. I think about this, right? X is a what? X is not a fixed number, right? Or is it? Yeah. So my question really is, what is x? That is not clear. Yeah. No, but assuming the sequence for what? Assuming a sequence for f of x. Uh, assuming what does that mean? Assuming a sequence for f of x. See, f of x is. Mhm. No, but f is a random function. You don't know what f is, right? You can take some sequences on the inputs, not on the outputs, right? Right? You can control the inputs, right? You can say that this input I will tend to infinity by xn equal to 2 to the power n, or xn equal to n square. Different ways, but you can't control the output, right? Right? That is not yeah, you can't control the output. Yeah, this is much more delicate, a little more delicate. Okay, let me come back to this question. Is this question okay? Is this theorem okay with everyone? Okay, so when we are converging to a point, when we are computing the limit at a point, right? Then the thing is saying that this limit exists around L for any epsilon. You are inside this. It means that for any sequence, when you take any sequence and approach A, then the output values will approach L, which is very obvious, right? But the other direction is also true. If it's true for all sequences, then the limit will exist. Okay. So yeah, and let me not prove that now, okay, because otherwise we'll have to go back to that theory. I mean, it can be done in a way that everything looks very obvious, but it takes a lot of time. So let's not go into that. Let's assume this, and then so basically the problem now is we will show that. So you can even forget about the question now. Right? It's kind of like he's trying to show that for every sequence it happens. So we want to understand the statement. Okay, we want to show that for every sequence this happens. F of xn goes to okay infinity. Sorry, it goes to 1. Yeah. So think about this. How can we do this? Yes. That makes sense, yeah, but we will not existentially prove. It kind of we will do it by contradiction. Yeah, we will do it by contradiction. Okay, so you want to say that you want to show that f is bounded. Uh, that does not. But if you want, you can show it at 0 only. Right? I don't mind. It's the same thing. No, but how will you show the f is bounded? Yeah, I think this is important here. Hmm. Okay. Okay. Mm-hmm. Mm-hmm. Yeah, yeah. That's right. That's right. That's right. That's right. Basically, this is it's less than 3. You can just write 3 because it's yeah for all x. 1 minute. Yeah, no, no. But let me just keep it there only for the time being. It doesn't really matter. Yeah, for all x bigger than let's say some m. Yeah. So this. Yes, but that did not really give any new insights. I'm just sticking with this. We can simultaneously write it and work and see. It doesn't really create a much difference, I think. But yeah, let's see. So let me first. So it's very important, and there's a very important point. We want to show that f is bounded, and this is important actually. Okay, it's very very important. This will be used here. Okay, because for those who want to understand the analogy, and I've seen Bolzano Weirstrass, for every bounded sequence has a convergence of sequence. Okay, that's what we'll use. We'll see how if you can't figure it out. Okay, so to show that f is bounded is very simple because fx plus 1 by fx will be less than 3, right? Because the limit is 2. So for any epsilon, you can take epsilon to be 1, right? A limit of hx. So hx, um, no, so this is slightly incorrect. I should say that this this will be less than, let's say less than 1 for all x after some point, right? So after some point, the function minus the limit is less than the epsilon. Okay, we know this. And then from here, you can show that f is bounded. You can show something. Will not be difficult. You can, as you said, take some quadratic equation. Yeah, and you can do several things and show. So you can do this. Okay, for all x bigger than m, and then for x less than. Okay, okay, yeah. So so then we should do it. Okay, so for all x bigger than m. Okay, so for all x bigger than m, we can say this. Obviously, not for all x. After some point, only it will happen, right? That it becomes close to 2. Okay, so from here, mm, mm, uh, yes, yes, no, but that will be the same thing. No, but from here, you can directly say, right? I mean, you can say that you can say. I mean, I'm just saying if you can say yes, but you can just say directly. You can say that if fx is more than 3, then this quantity becomes more than 1. That's a contradiction, right? If fx is more than 3, then f plus 1 by f minus 2 is more than 1. And so its mod is also more than 1, which is a contradiction. So we can say that fx is less than 3. And so it's bounded. So f is less than 3. Yes, yes. Why did I take 3? I don't know. It's just to be safe. But yeah, you can take it to be 1. You should take it to be 1. So you understand that that's very simple. That's just a computation you can do. Okay, so I'm not doing it. Yeah. So f is bounded. So let me in fact remove all this and just write f is bounded. Okay. But you must check it. You must write it and check it. So let's write it here. F is bounded. So f is bounded. We have shown. I mean, it's very clear from here was what we have shown. Okay. Okay. Now what do we do next? Yes, yes, because already it's positive and so on. Yeah, something else. Yes, some maybe discriminant or something. Yeah, anyways, yeah, we have shown. Okay. But now we want to show that any sequence you take, fx has to go to 1. How do we do this? This looks very strange, right? So any sequence you take to infinity, we are saying that fx has to go to 1. So you take x1, x2, x3, and so on. And this is the line, this is 1. And we are saying that if you track the function along this sequence, it will eventually go to 1 if this is a sequence values, anything. Yeah. So any xn could be n square, xn could be to the power n, xn could be 2 to the power n, anything. N times sine x, anything. Sine n, n times sine n. So this is the sequence. So remember, you guys know that this is a bounded sequence. We have already shown f is bounded. This is a bounded. Now all of this looks very longish, right? Very long proof. In fact, it's because we don't have the right uh, language yet, which once we develop, the proof becomes like few lines, maybe. Yeah. But right now we have to do it like this and learn the things. This is the sequence. We want to show it goes to 1. It's a bounded sequence. F of x1, f of x2, this is the sequence, right? It could be f of 1 square, f of 2 square, f of 3 square. Like in what sense? Uh, I don't know. You have to be more precise. I can understand what you're trying to say a little bit, but try to be more precise and see. Yeah. Adish, you are getting anything? You're saying something? Hmm. Hmm. But in general, that is not a true statement. It might work in this case, but generally that's not a true statement, right? You know that. I mean, some of, yeah. This is less than epsilon. Okay. Uh-huh. Okay. Yeah, we can remove the mod. Okay, this looks like a good idea. Divide by m on both the sides. Okay. Sorry, I didn't get f by mod of f of x. Okay, so fx is less than m. Okay, 1 minute. I'll just change my location. Just give me 1 minute. Yeah, so you're saying on the left hand side you replace. No, but you can't replace it on the left side, right? Can you replace it on? Can we do that? No, right? Yeah. Yeah, 1 by, yeah. If you do 1 by, you see, you cannot do that. Because this will be less than f square plus 1 minus 2 by f. But then there's no guarantee this will be less than this. Yeah. Yeah, we want it, but it doesn't. Yeah, if you. No, but your idea can work. I think your idea can work. I mean, what you're saying is if you instead do like this, so this is a slightly different approach. If you do like this, uh, as you did, so as you did earlier, if we just do this, so we know that this limit is 0, right? Yeah, this, no, this, no, this limit is, the limit of this is 0, this thing. Then how do we, so limit, yeah, but that's again a problem, right? X goes to infinity, this thing is 0. But we don't know if limit of this. Uh, okay, can you say it in this context? Xn. Okay. Okay. So let me create a bit of space and then, yeah. So first of all, we are getting this because this is what's given to us, right? We're just taking things to one side and taking. No. I'm taking the 2 this side. No, that's how I wrote it. Okay. So what you are saying, Adish, here, uh, this is. Uh, okay. So you are saying this thing by fx, this is less than. Oh, sorry. Yes. Yeah. Right. Hmm. Hmm. Right. No. So you're saying that I can write fx here also. Hmm. 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 No, there's no need to. This is simple. This is just sandwich theorem. Yeah, because m is positive, you can assume. I mean, yeah, m is. Um, right. So this was the, so basically this initial manipulation, right? This initial manipulation that we did, right? That is helping us come to this and the boundedness, which Adish kind of came with. And this is, I think, Raghav's idea to begin with. So two different ideas basically from two different people. And then, yeah, then it's very nice, right? Yeah. Okay. So we had this, right? And we wanted to work with this limit, right? And then you kind of just divide it and Yeah, this is just inequality, and then by Sandwich theorem, it goes to 0, right? So we know that this goes to 0, and so f of fx has to go to 1. Does everybody get this? This is an alternate proof that I didn't plan, and I didn't know of this proof. I mean, I had not proved it this way. Yeah, so just take a minute and see if there are any questions in this. Okay. Yes, yes, that's right. That's right. Yeah, that doesn't really matter. That's right. Yeah. Constants will not matter. Right? So we didn't have to take the sequence approach actually. Okay, we didn't have to take the sequence approach. But the thing with this question, the way we have done this is it's kind of based on manipulations, right? It's kind of based on algebraic manipulations, and you don't know if that will always work, right? Completion of squares and so on. Okay, if that does not work, then what will happen? I don't know. So let me still go with the alternate proof which I had in mind, and I will say it. Yeah, let's say this. This was a very nice proof based on. This is the way maybe it should be done. If you let's say are in high school and you don't know any theorems, if you do it the hard way, that was a slightly. But we did show boundedness, which is also useful. But you see, the point is that we want to show that this limit. So coming back to my approach, even yeah, but let me come to this. We want to show this limit exists, right? Assume it doesn't exist. Assume f of x and limit does not exist. Yeah, so there is a sequence, it's bounded, but the limit does not exist, right? Now we know that there will be a subsequence whose limit will exist. Okay, a subsequence. Now, subsequence we know is just a part of the sequence which you take. It's infinite, but you take by skipping some terms. Okay, but there will be a subsequence whose limit exists. Now, this again I have not discussed with everyone. I will do it properly next time, maybe, or not next time, but we are cycling through this topic again later, then we'll do it. Okay, but yeah, this is the result. You can assume it for now if you don't know, but there will be a subsequence limit exists. So any bounded sequence, the point is that any bounded sequence, which is, it can be very wild, bounded, but it's bounded. Okay, then basically there will be a part of it which will be monotonic. You can kind of find out either a monotonically increasing or a monotonically decreasing part, infinite part, which is monotonically increasing or decreasing. And that will obviously have a limit, right? It will go towards one place. Okay, that's what we are using. This is the Bolzano Weirstrass theorem, right? You were there, yeah, we had done this. This is called the Bolzano Weirstrass theorem. I can just say that, yeah. Right, okay. So then what can we say? So then we can say that, so if this limit, so this limit, we want to show it exists. If this limit doesn't exist, no problem. There will be a subsequence which will have a limit, right? Now you see, for any subsequence, okay, any subsequence you can take I1. This indexing gets a little complicated, but this is a subsequence, and this limit exists. Okay, a limit of this exists, right? We will put it on the front. Okay, then what should this limit be? 1. You can just put it in this equation, that xi1, that limit. You can take the limit along that sequence, it will be 1, right? That limit is 1. Right? So you are assuming that the limit of this sequence does not exist, but then we know that there is a subsequence of this along which the limit exists, and that limit is 1. Okay, can we say anything more? We can say that any subsequence, any subsequence of the star which has a limit will go to 1. Mm-hmm. X1, X2, not F. Yes, yes, yeah. They, obviously, they go to infinity, right? Because mm-hmm, mm-hmm. Yes, they are included in the sequence, and they also go to infinity. Yeah, yeah. So actually, it does follow, but then you have to reason it. So I'll say the roughly the reason. Okay. See, if this limit, and then I will say this purely in terms of sequences without f. Okay. See, the point is that xn going to infinity is not a problem, right? We want to say that this limit exists. Now, you see, if this limit does not exist, okay, and if the limit is not 1, it means that there is a subsequence of this which does not go to 1. Is that right? Yeah. If this limit does not exist, it means that there is a subsequence of it which does not go to 1. Right? Yeah. But okay, no. But wait. Hold on. So there's some confusion. So we want to say that this one exists and it goes to 1. Yes, yeah. So let me say this very, wait, where should I? Okay, yeah. So if this, I'll just first say it in words, okay? If this one does not go to 1, if this one doesn't go to 1, maybe it doesn't go to anywhere, right? Then it has a subsequence which goes to a different number. It converges to a different number, right? But then you can take a subsequence of that subsequence that converges to 1, which is a problem. Or you don't even have to go there, right? If this is, yeah, so let me just say it as a sequence, okay? First, yeah. So if y1, y2, y3, and so on, okay? We want to show that, let's say this goes to 1. This is kind of what the problem is. So show that this goes to 1, okay? This goes to 1, given that every convergent subsequence, every subsequence that converges to 1. So the subsequence that does not converge, we don't know, not given, but every convergent subsequence goes to 1. Goes to 1. So what I'm saying is that it is not given that this limit exists. It's not given that every subsequence has a limit. For example, this, I cannot give a concrete example because no such example exists, because eventually the limit will exist of y only, y1, y2 only. But hypothetically, this limit may not exist. Yeah. If it exists, but if it exists, it has to go to 1. That is what is given to us. Okay. And from here, this is an exercise in sequences, but we will do it now. Every subsequence that has convergence, that converges, goes to 1. Then yeah, that's now we want to show this. And let's assume that this is bounded. Okay? We actually don't even need to, but let's assume that. You don't need this, but let's assume it. This is kind of the story of the previous problem, right? That every convergence subsequence of f of xi was going to 1. So let's do this in a clean way here, and then we can understand this as a result. So every subsequence that converges to 1. You want to show that the whole thing converges to 1. Yn minus 1 is lesser than. We don't know anything about the y's, right? No, we don't know anything. Okay. If you assume this, yeah, that's right. I mean, if you assume this m, yeah, but that will not be. This will not be useful, right? I mean, you can say things. No, you cannot say this. You can say m plus 1 or something. No, but this bound will not be useful for the. Yeah, think this thing. This is a very good problem, actually. It's not hard, but it's a little confusing sometimes. So it's kind of every sub part that converges to 1. To 1. No, so that is not true. That is not in general true. So for example, you can do this example. You can try this. This is it's a very good exercise. So you can take yeah, so you can take a sequence of sequences. Okay, so you can take this sequence x1, x this, and let's say this. So you take this sequence. Let's say this goes to 1. Okay, and all of you can try this for homework. This is a good exercise. It's asked in, I think this was in some of the some fest of ISI, some integration fest. I think this question was there. So this, but yeah, it's a famous result. And so all these sequences go to 1. Okay, so you can understand what I'm doing. This is another sequence. So this is not square. This is just a indexing. Okay. All these infinite, so they're infinitely many. Okay, infinitely many go. Okay, goes to 1. Now, if you combine these to make one sequence, now how can you combine it? You can combine it in many ways. But for example, you can combine it along the diagonal. You cannot come. Okay, you can take a piece of it along the diagonal. You can also combine it in interesting ways. You can. So I can say this: if all these go to 1, show that it is not necessary that this sequence, which I am traversing like this will also be a sequence. Remember, right? This will be one sequence. Okay, the blue sequence need not go to 1. Blue sequence, and make an example. So the first one goes to one, second one goes to one, but if you combine them like this, you can get a sequence. Okay, this is a hard question maybe, but I'll give an easier version also. But first, you can note this down. So you see how the blue sequence makes up a sequence. Right? You can just along this pyramid kind of, it's a sequence. You can explicitly write the formula, but that's not needed. Some sum of natural numbers and so on. Okay, but simple version of this is show that this one, this is also a sequence, right? X1, 1, X2, 2. This pink one also need not go to 1. Pink sequence. In fact, it's enough to do the pink one only because that's a subsequence. But anyways, yeah, just do it. Just do the pink one only first. Pink sequence need not go to 1. It's kind of like combining, but the combination did not go to 1. And you can think of some mathematical reason also. It's not difficult. Just find out different sequences that go to 1, kind of in a pattern, and try to do. Okay. No. For every epsilon, no. First step to say for every subsequence. First step to say given a subsequence. Right. Okay. Given yi1, yi2. So this is a sub part. So this is just I1 less than I2 less than I3 and so on. Yeah. Given this converges, yeah, then yes, eventually, yeah. So yeah, so given epsilon greater than 1, after some point means that there exists the n naught, right? There exists an n naught such that for every n naught, for every n after that n naught, the terms, yeah, that becomes very tricky to write. Yeah, maybe I can write like this. After some point, all I'm trying to say is that after some point, this is less than 1. This distance from 1 is less than epsilon. This is just the definition. Yeah. But how do we use this? Hmm? Yes and no, that's the problem. Every term will be part of some subsequence, but will be, but that subsequence need not converge. Right. And also, even if it was, that's still a problem, right? Because different, and that's the spirit of this problem also. Problem is that different convergent subsequences will converge at different rates. Right. And so if you combine them, you have to negotiate with all the subsequences. And the rates, if you negotiate with everyone, that rate might turn to infinity or something. You may have to take larger and larger n naughts, and then eventually you will run out of natural numbers. I mean, you understand, right? Like they converge at different rates, right? Like, yeah. Intuitively, that is the idea. So it's combine, and it's not so hard also. It's not this hard. It's actually a very simple argument using. So if you just use the fact that there are enough convergent subsequences. So as a hint, or rather, this is the thing that this is the deep fact about the real numbers, right? That every sequence has a convergent subsequence. Every sequence has a convergent. Yeah, anywhere you go, it may not converge, but there will be a part of it that will converge. This is the deep fact. This basically, yeah. Yes, yeah, bounded, right. Yeah, bounded I should write. Basically, this is saying that there are enough real numbers, right? There are enough sinks. As long as you are monotonic, you will converge somewhere. Mm-hmm. Mm. Infinite monotonic. No, that's not true. Yeah, but eventually, yeah, it is not true, and but it will be true in some sense, but that gets very delicate. Is that eventually every term will be there, meaning that every subsequence you take, then eventually kind of like that. Basically, I'm saying that every subsequence has a subsequence. Yeah, that's roughly the idea, but then it gets very delicate, and this problem is much easier. So, see, all this is saying is that look, just say that if y1, y2, dot, dot, dot doesn't go to one. Let's draw a picture. I think we are just making it more and more abstract. Let's draw a picture. Yeah, and for those who have not done Bolzano Weirstrass, I'll do it later. I mean, I'll also give you some references you can see and watch, but I will also do it. Okay, so don't worry about that. Uh, yeah. Let's say this is the number one, right? Now, if this sequence doesn't go there, what does it mean? It means that it means that there is some epsilon, it means that there is some degree of closeness which this sequence doesn't attain. Some degree of closeness to the number one, which this sequence refuses to attain, right? It means that there is some epsilon, or you can just say, write the contrapositive of the statement of the definition. But roughly speaking, some epsilon is there such that when you take this epsilon, okay, just give me 1 second. Can I say it in an easier way? Yeah, I can, yeah, I can just say it like this, right? I can say it like this. If this, so basically I'm saying that I can say it in another way. Let me first say it in the easier way. See, if this goes to, we know that, so we know that if this goes to one, that implies that, so focus on this point. Just for a second, just do this thing. For a second, assume it does go to one, okay? And then what happens? If it goes to one, then every subsequence, right, goes to one. That's right. Yeah. All of us know this, right? If sequence goes to one, then obviously every subpart will go to one. But the converse is also true. Every subsequence goes to one, meaning that this goes to one. I'm not saying every convergent subsequence, just saying every subsequence, right? If every subsequence goes to one, it means that this also goes to one, right? But then it means that if this does not go to one, then there is some subsequence which does not go to one. Right? Yeah, but from there, but actually it comes down to the same thing. I have to say this one. Yeah, it just comes down to the same thing. Sorry. Yeah. So let me not go into this. I mean, you can probably write it from there also, but just to say it very clearly, let me just stick to this. So if this does not go to one, my point is that it will go somewhere else. This is what I'll show. Okay. This means that given this epsilon, nothing works. No and not works. Okay. Given some given epsilon, given, so there will be some epsilon, not given. There is some epsilon greater than 0 for which no, and not works. Nothing works, which means that you take 1, it doesn't work. There is an x1 bigger than that. Yeah, for 1 there is an x1. For the number 1 there is an x1 bigger than 1, such that wait, I should not say x1, I'll just say I1. Okay, I'm not saying x1, I'm just saying I1. There is an I1 bigger than 1, such that y of I1 is bigger than 1 plus epsilon. Okay, or it is lesser than, it is outside the band. Okay, so the number 1 does not work. Okay, meaning that if you take 1, then there is some term after that for which the sequence pops out of the band. Okay, and you can do this for all numbers. Let's do it. So the number 1 doesn't work, which means that, let me write it crisply, such that there exists I1 such that yi1 minus 1 is bigger than epsilon. Okay, similarly for the number 2, if you take 2, then the 2 also doesn't work. If you take 2 as a naught, it doesn't work. Because after some point, after that, there is some number where it again goes out. Right? It just keeps going out. There is exists an y2 such that this also goes out of the band. So this was a band, but my point is that eventually the sequence is not inside this. So you keep going down, right? You keep finding terms which are outside. These are your subsequence, which is outside, completely outside. Okay, so now what does it mean? You get a sequence yi1, yi2, yi3. You get the sequence, right? This sequence, what can we say about this sequence? Yeah, the mod of this sequence is always at a distance of more than epsilon from 1. So how can we use this? Yeah, so we know that yik minus 1 is more than epsilon. This sequence is always outside the epsilon band. So there is no way it can converge to 1, obviously, right? So it cannot converge to 1, but we can say something more. No subsequence of it can converge to 1. Yeah, right. So, yes, right. So the main thing is that no subsequence, not of the y's, not of the yi's, but of this yi, these things, this subsequence, no subsequence of this subsequence. Okay, no subsequence of this can converge to 1 because its distance is always more than this epsilon. Subsequence of this, no subpart of this, even of this, not even of this, can converge to 1. Yeah, that's right. Yeah, it will be a subsequence of this, which is a subsequence of the original. So no subsequence of this can converge. There will be, yeah, that's right. There will be some subsequence which will be convergent, right? That's right. Yeah. So basically what you said is, I'll just write it, but no, it's just two-step different descent. It's not infinite descent. I will not agree. It's a different, yeah, that's much different, I think. Yeah, but there is some subsequence of it, some subsequence of uh, of this, right? That is given in our question, that converges to 1. That's a contradiction, right? Why? Because there will be some subsequence of it which will converge to 1. Now that's given to us, so we really cannot. Yeah, that's given to us. We cannot push it. Right? Yeah. Right. There will be some subsequence of this. Hmm. Hmm. No, 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 no. Length is not, you're reducing the complexity. Length actually may not decrease. Length actually may remain infinite. Right? You can take a sequence of odd numbers or multiples of one, then something you can just take different varieties of things. Right? You can keep getting infinitely many copies. Right? But yeah, but the complexity is decreasing. Right? Initially, we didn't know where all it can go, but we know that there is a part of it that is like this. Then inside that part, so we're reducing the complexity. We're taking intersections and right. So we are kind of crucially, we are using the fact that every sequence has a convergence subsequence, right? Because this is a subsequence and it has a convergence subsequence, right? But then subsequence of this is a subsequence of the original one. So it has to go to one, which is a contradiction. But we have to use the fact that that everything has convergent subsequences. Mhm. It may not be much more faster approaching, but it will be at least as fast. But we cannot say much faster. Yeah, but it will not. Yeah, in perspective, it may look, but if you just traverse along, it will not look like that. Yeah, it may not converge faster, but the point is that we will be surely able to say that it converges somewhere, right? And those are the things. That, okay, I mean, the point it's actually a very delicate matter. I mean, we use the theorem, but it's a very delicate matter. See, the point is that we are using the fact that the point is that we are using the fact that every sequence has a convergence of sequence, right? What is this saying? This is basically saying that the real numbers have enough things. R has enough elements, right? That R is constructed in a way that it doesn't miss out anything, right? So if you are traveling in a certain way, right, then you can find a part of it which does sync somewhere. That R has enough things, okay? But from studying the subsequences, we are able to say that the limit of the original sequence exists. Right? So that's kind of the reverse, right? By 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 knowing the nature of all the subsequences, we can say about the original sequence, right? Or by knowing the nature, or by traversing, by not by traveling to zero in along all possible sequences, that is enough to know it in the entire neighborhood. You see, sequences are countable things, right? So by studying these countable things only, infinitely countably many of these countable things, we are able to understand R, which is uncountable, which means that R doesn't have too many elements. Right? So by studying subsequences, we are able to say about the sequence, or by studying sequences limits, we are able to say about the limit of a function. This means that R doesn't have too many things. R does not have too much. That's why R is perfect. R is just the right things. Okay? It doesn't have more than what is needed, but it has enough. Okay. Yeah. So R is just the perfect thing. This is basically saying that the rationals are dense in the reals. If you go to the proof of why all subsequences converging imply this sequence converging or those kind of statements, you will be using the fact that basically like Q is dense in R. Okay. And Bolzano Weirstrass is saying that R has enough elements. That's how you see the construction, which maybe you have not seen, but we start with Q and then we add things to make this happen. Yeah. But anyways, let's not go into more things now. We'll go into more relevant stuff next time. So yeah, this is what I wanted to do. Okay. But really, this is not a good. We did it, but it took a long time, right? But if we look at this question again, okay. If you look at this question again, there is this concept, right, which we are roughly stated once, is of a biggest limit and a smallest limit. Okay, so assume, now this I'll say roughly, assume that limit of f, let's say we don't know what the limit of f is. We don't know if it exists, right? Okay, let L be the biggest limit. Now this we have not yet defined, or if such a thing is there or not. But for a time, if you assume that L is the biggest limit and small l is the smallest limit, be the smallest limit. Okay, I will show that these two are the same, then I'll be done. If the biggest limit is same as smallest limit, then because there is something, right? If you generalize the sense of limits, right? So limit means when you goes to one place, right? But if you basically travel along different sequences, you approach zero by using different sequences, or to infinity using different sequences. That doesn't matter. It doesn't really matter. If you approach to infinity using different sequences, and you get different limits, right? You take the biggest of all those limits, and then you take the smallest of all those limits. Roughly speaking, right? If I can show they are equal, then I'm done. Right. So if the biggest limit is attained, if this limit is attained by, let's say, this sequence, x1, x2, and so on, and the smallest limit is attained by approaching along this thing, yeah, then if you put them in this, you will see that they are both the same. Yeah, you can just put and check. You see this limit. So this you are putting, you're traveling around that sequence which takes you to the biggest limit as n goes to infinity. Obviously, I mean that f of xn will exist because that's the biggest. If you like go to the biggest limit, right, you will get L plus 1 by L is equal to 2. From here, you get unique solution L equal to 1. But if you do the same thing for the smallest limit, you'll also get 1 because it has unique solution. You see the point, right? Because it has a unique real solution. Yeah, the smallest limit will also have the same equation, so they both have to be 1. Right? Now you can kind of see, right, if you have any polynomial that f satisfies, and if that polynomial only has one real root, if that polynomial has only one real root, it could be some complicated polynomial. It could be, I don't know, x squared plus x plus 1 divided by x to the power 100. This has only one real solution, and you put f there. You can put f, make a very complicated question. You can take much more complicated things. But as long as that polynomial has only one solution, you can do this capital L small l business, and you will get that they have to be the same and the limit exists. Okay? But the point here is, so till now we don't know if these things are real or we just imagine. Like, what is the biggest limit? Is there any such thing as getting to the biggest limit of a function and smallest limit? And can you actually get there by using sequence? Yes, we have proved that because of the nature of this equation, because of this AMGM x plus 1 by x equal to 2 means x equal to 1 equality case, or you can say in terms of polynomials, because this polynomial has a unique solution, f of x minus 1 whole square equal to 0 means fx equal to 1, right? The same kind of things, right? Because this polynomial has only one solution, the biggest and the smallest limits at, yeah, in general, they are not the same, right? In general, they are not the same, right? Yeah, they tend to infinity. For be a, yeah, but but we are getting different limits. So if because in general there can be many limits. Yeah, if you extend the sense of limit. Now what I'm saying by extending the sense of, I'm saying that take different possible sequences to infinity and you get different sequences of fx's, right? And they may tend to different places a priori. Take the biggest of those and take the smallest of those. Okay. So this xn goes to infinity and this goes to infinity. Okay. But f of xn goes to L and f of yn goes to small l. Okay, so different possible sequences going to different places. I'm taking the biggest and smallest of them and I'm showing that they are the same. So then there can be nothing in between. So it means that all sequences, it must go to L. But for this, I need to show that such things actually exist. Why should there be a biggest limit and there be a smallest limit? And those things one has to show. Okay. But this is a much more sleeker proof. This is the way it should actually be done. Like no manipulations, it's a conceptually tight proof. Right? Okay. If you have, mm-hmm. Mm-hmm. Yes, no, this theory is actually not tough. This theory is not tough. I mean, it can be done in a very clean way. It depends on how it is done. Yeah, I mean, this basically biggest limit and smallest limit one has to show. So basically, the limit of a limit is also a limit, and that's why there is a biggest limit. But yeah, that has some concepts have to be introduced, then it becomes simple. Yeah, because then you can prove something much more general, right? That if G is a function, okay, and G of fx equal to 0 is an equation, and it has only one solution, kind of. There is only one f, right? Like in this case, G is G of y equal to y plus 1 by y. If the G is injective, then an f satisfies this limit. And if limit of G equal to 0 as x goes to something, then limit of f will also be existing and you can find it. But there we show that they are the same. Yeah, but there it is the same for two reasons. That there the biggest and the smallest limit is the same because it is actually related. Yeah, it is the same again. It is because of that continuity of f. Okay, on that level certainly. On that level certainly. Right. Yes. In that sense, that's a very similar idea. It's a bit, yeah, basically it's a fundamental idea, right? You show that something exists by squeezing it between two things, and that's also basically we are showing. Yeah, that's right. Okay, so we will do the next class on Saturday, and on Saturday we will do the concrete things. Okay. Yeah, today also we did concrete things, but yeah, okay, Saturday we'll do concrete things. Mm. Okay, and that's it for today. Thank you. Huh? Yes. Sorry. Yeah, and the third one is more conceptual. This is like a third proof, right? Okay, it's not a proof, but it's an idea. Yeah. Yes. Yes, I will also start integrals. Yes. Yes, but how do we do it? Yeah. I mean, we can write now. We can write a proof using all that we have done. But yeah, so you can say yes. Okay, m plus 1 by n. Why? Oh, but capital M is the upper bound of f, right? So f of x minus 1, its mod, this could be bigger than m, right? Much, it could be bigger than m plus, it could be m plus 1 around. It could be negative, right? Or it would be m plus 1. Or no, but in our question, it was not the case, right? Yeah, it was not negative, right? No, no, but okay, okay, let's assume this. Okay, then. No, how is it lesser than epsilon? M is, you don't know what m is. Which 1 by n, yeah, but m we don't know, right? Yes, because it should work for, but m can be big, right? So this is not true, right? M plus 1 by n will not be less than epsilon. I mean, epsilon can be very small, right? And m you don't have simply. It's not about big and small. It's the fact that you don't have control over m, right? And neither do you have control over epsilon. So you don't know. Given any m, even if m is small, you can take a smaller epsilon, and then we are gone. Right? It should work for every epsilon, right? So it will be very difficult to write a proof using epsilon using the definitions. You have to go a long way to then actually prove Bolzano Weirstrass and everything, maybe, which all can be done, but I cannot. We don't. It's difficult to do. Okay. Yeah. So maybe yeah, Friday we will do start with a little bit of not yeah. Let's see. We'll start with integration maybe. Okay. We'll do not Friday, Saturday. Okay. Any questions? Any questions? Anyone has? Okay, okay. Thank you then. Thank you. Bye. Thank you.